And now jumping to the FSK Demodulator when it is using the PLL or the phased locked loop. We say that the PLL is the most commonly used circuit for demodulating binary FSK signals, and it takes the shape as shown in figure 912. And we just see, I have added a video called phased locked loop tutorial that just describes to you, in case you have forgotten, how the phased locked loop works. And therefore I will not go into the details to describe how that works. Therefore, what I will just say is that consider you have an FSK signal at the input of the PLL. It has two frequency components, F1 and F2. And as you know, this block of the PLL just detects the difference between the input signal, or the one that is also called the reference signal, and the one that is generated by the VCO, or the voltage controlled oscillator. I have renamed this diagram because I don't think this is the appropriate term. The PLL has three blocks: phase detector or phase comparator, the VCO, and the loop filter, also called, sometimes it may be also called the amplifier. So when the phase detector detects that the input signal is F1, it will try to trigger the VCO to generate a signal whose frequency component is as close to F1 as possible. Now, when they try to do that, there will be some DC voltage that will be detected, and that DC voltage can be equated to a signal that is representing either a symbol 1 or a symbol 0. So we can say that when we have F1, we are going to detect some voltage that is equivalent to, that can be taken through the decision-making device to classify that signal as a 1. And when F2 is detected, then the phase detector will notice the difference. Try the loop filter will try to tune the VCO or the oscillator towards adjusting to F2, and therefore there will be some voltage difference that will be generated by the loop filter, and therefore that voltage difference can be considered to be equivalent to V2, and V2, when taken to the making device, it will classify the V2 as simple 0. And therefore, we are going to have a sequence of zeros and ones. When we have F1, we represent that as 1. When we have F2 or F0, we represent that one as 0. And therefore, we end up receiving our originally transmitted binary sequence. And now very quickly, we talk about the advantages and disadvantages of FSK. And we see now that the transmission bandwidth for BFSK is the same as that of ASK, and we have seen that in our earlier lecture. FSK is less susceptible to errors than ASK, because if you remember that ASK is dependent on envelope detector. When we are the DC component is changing from some voltage, positive voltage, to 0, and vice versa. There is a likelihood of error introducing some error in the amplitude, and that simply says that ASK is more susceptible to errors than FSK. Now, it has better noise immunity than ASK in similar manner. The peak frequency offset is constant and is always a maximum value. We are saying that F1 minus F2 is always constant, and therefore we are always going to be experiencing a maximum value of this frequency offset. Now, finally, the highest fundamental frequency is equal to the half the information bit rate. In addition, the probability of error reception of data is quite high. We will see what is the probability of error that is generated by FSK. And finally, we are going to say that FSK is relatively easy to implement. As you can see, you can very easily do it using two local oscillators that with F1 and F2, and simply get two components that are representing the binary zeros and ones. Some disadvantages of FSK are as follows: that FSK is not very efficient in terms of bandwidth requirement, and I think we have seen that it requires 4 FB, which can be huge compared to the ASK. FSK has a poorer better performance than PSK and ASK. We also see that the probability of error, or the error performance of FSK is better than that of ASK, but again it is inferior, or it is less than that of PSK. PSK provides superior performance than FSK. We have not yet looked at PSK, therefore in a subsequent lecture we are going to look at that. But we should just note that PSK or QAM, and we are going to be looking at that, is going to be, it has poor, okay, the FSK has poor performance than these two. So in terms of application, we should note that FSK is generally used in low-speed modems up to, or with the ones with up to the speed of 1200 bps or bits per second in over analog voice band telephone lines. It is also finds application in pager systems, and therefore high frequency radio type transmission systems and local area networks are also very or also find some use for FSK. That is some other areas in which we use FSK.